All right, so where we left off was with the randomness characteristic of a pseudorandom number generator. We talked about, the test, the NIST SP 800-22 test, where we're basically trying to establish three characteristics of the randomness. Number one, uniformity; two, scalability; and three, consistency. And we said uniformity is basically meaning that we want to have roughly the same number of zeros and ones in our generated random sequence. In other words, 50% or close to 50% of the values should be zero and the other should be ones. In terms of scalability and what that means, so we want to ensure that not only is the entire random sequence basically random, but we also want to ensure that any subsequence of it is also random. In other words, if I move down here on the whiteboard, let's say I have a string of 100 bits. Although this is a very small number, we generally, generate random sequences within thousands of bits. But, just for the sake of simplicity, if I take, 20 bits over here, these 20 bits will also look random inside this 100 bits. If I take another 20 over here, this subsequence of 20 bits will also be a random value. Now, the good thing about this is that it ensures that you don't have to necessarily take the entire generated stream of bits to be random. You can take any subsequence that you want of it, and it will also be a random one, depending on what your application is. The other factor here, consistency, is the definition that this behavior of the pseudo-random number generator, and by that I mean uniformity and scalability, should not necessarily be true for a certain input or for a certain seed value. For any seed value that you give it, the generated string of bits should have uniformity and should have scalability. And if that happens, then we basically have consistency. So consistency is referring to the consistent behavior of the pseudo-random number generator across different values for the seed and not just one specific value. So if we move to some randomness tests that we do, there are basically 15 tests inside the SP 800-22, which can be sort of categorized into three different sort of tests that we apply to the pseudo-random number generator in order to ensure that it maintains those three characteristics. The first one is the frequency test, which relates to the uniformity test. And it's basically saying that, the purpose here is to determine that the numbers of zeros and ones is approximately the same. Now, they won't always be exactly 50%, but close to 50%, or as close where we can get it, is what we're looking for. The runs test, this is basically, focusing on the total number of runs in the sequence, where by run we mean an uninterrupted sequence of identical bits, like a sequence of, say, 10 zeros or 10 ones within a random string that's longer. It's a variable length. So what we mean by that is that, if we were to say we have 100-bit output here, then the length, let's say this length is all zeros, and this is 5 bits. This is all ones, and this is 5 bits. We don't want all of these to be 5 bits, 5 bits, 5 bits. In other words, we want the next one over here, let's say, to be 17 bits of, say, zeros, or, we want it to be the next one, maybe, I don't know, somewhere in here being, 25 bits of zeros or ones. But we don't want them to be the same length, and we don't want them to be in the same place. So, we want to have, this is generally called a run. Each one of these is called a run. This is a run. This is also a run. So is this one. This is also a run. So a run is a subsequence of bits that are the exact same, all zeros or all ones. And what we want with the run test is to make sure that these runs have a variable length and they're scattered around inside this 100 bits. They're not all of the same length, they're different lengths, and they are spread around in these 100 bits, or whatever the length of your generated sequence is. The next test that we do to ensure that it is the pseudorandom number generator is generating a random string of bits is Moore's universal statistical test. And the main focus of this is the number of bits between matching patterns. So if you say, if I have, like here on the whiteboard, I'll show you guys, if let me move down here a bit. If I have a sequence of 100 bits, and over here I have a let's say a pattern of 1 0 1 0 1 0 1 0, and again over here I have a pattern of 1 0 1 0 1 0 1 0. So these two patterns are the exact same. And in between, I have another string of bits. These could be anything over here. The idea is, how well can I compress these 100 bits without losing information? I'm not going to go into the whole compression algorithms and what the definition of information is, but generally, if you can compress a sequence of bits, in other words, make it shorter without losing any information in there, then that sequence of bits is not very random at all. In other words, if I could say, if this 100 bits over here, I can compress this with a compression algorithm to say only 50 bits. And if I decompress it, I can get the same 100 bits back. Then that means there was not much randomness in this 100 bits to begin with, right? So what I'm looking for is a stream of bits that are so random that whatever compression algorithm you apply to it, you still have something close to 100 bits, like say 95 bits is the output of the compression algorithm, or I don't know, 90 bits, or even better, 99 bits, right? So, and this solely depends on the compression algorithm, but you get the idea. The idea is that you cannot throw away the bits in this 100 bits that were generated and come up with a shorter string of bits that, when decompressed, will generate that 100 bits of information for you, right? But we're not going to go into this too much. So Don't worry about it if it feels a little complicated. It's not something that we are going to cover too much. The most important thing that we're going to be sort of covering is the frequency test and the runs test. And more importantly, frequency is what we're going to be focusing on. So in terms of unpredictability, which was another feature or another characteristic that pseudo-random number generators um, had to have, there are two things that we're looking for: forward unpredictability and backward unpredictability. Now, forward unpredictability means that if the seed is unknown to a hacker, the next output bit in the sequence should be unpredictable, right? So, in other words, meaning that it doesn't matter if um, if you have 100 bits of your sequence already generated for you. If you don't know what the seed is, you cannot determine what the 101 bit is going to be, right? What the next bit is going to be. That's forward unpredictability. Backward unpredictability means that if you if it shouldn't be feasible to determine what the seed is from any sequence of bits that the pseudo-random number generator has generated. And this looks pretty obvious, right? Because what we're looking for in a pseudo-random number generator is that the hacker cannot determine what the seed value was just by looking at the output of the random number generator. We want it to be so random that they can't even guess what the seed was going to be. And that's basically what backward unpredictability means. You cannot move backward to from the output to the input and determine what the seed was. So that's in terms of unpredictability. Now, the other thing that we had for a pseudo-random number generator was seed requirement, right? Or the characteristics of the seed. So the seed is the part that we keep secret, right? We do not let it leak outside of the algorithm. It should be kept between the sender and the receiver. And it, like I said, it must be secure and it must be unpredictable. So it can't be something like, oh, I'm going to give the seed just a string of zeros. No, that's not a good idea. Or a string of one. No, you want the seed itself to be random. Now, usually what we do is the seed itself should be a random or a pseudo-random number. Now, to make things even more secure, they basically say that the pseudo-random, the seed should be generated by a true random number generator, right? So what we have when we talk about a pseudo-random number generator in general, we have an entropy source. This could be, you know, the clock on the computer. They could be, I don't know, a certain click on the, or, you know, the coordinates of a click on your computer screen. I don't know, a certain key that you push on the keyboard, but it's some source that is unpredictable. And that is fed into a true random number generator, which then produces a seed for us, or the output is called the seed. And that seed is then put into a pseudo-random number generator, and then we get our pseudo-random bit stream. And this is basically what we have for a pseudo-random number here. So this entire thing altogether is a pseudo-random number generator that we have. Now, usually they only talk about this part, you know, they don't talk about the seed generation because it's, you know, it would complicate things. So we're going to only talk about this piece over here. We're not going to talk about how the seed is generated. Now, okay, so we talked about what characteristics a pseudo-random number generator should should satisfy. We talked about uniformity, unpredictability, and the characteristics of the seed. We talked about the NIST test that you can run on a PRNG or pseudo random number generator to check and approve that it is random enough. But let's go talk about how we actually build a PRNG. What's actually used in things to actually build one. So the way we design a PRNG, and this is basically what we mean by this slide, algorithm design, there's basically two categories of design. So either we build a PRNG for a certain purpose, right? It's built to be a PRNG, or we use other structures that we know of to build a PRNG. So by other structures, I mean like, encryption schemes. Like we said when we were talking about modes of operation, some of the modes of operation, because the output of an encryption scheme, when the key is random, the output is also random. We can use the output as a random source, we can use the output as a random stream of bits, right? So that's why here we have like symmetric block ciphers. We can also use asymmetric block ciphers, hash functions and method authentication codes. We'll get to those in the next few chapters, and you'll see what those things are and how they can be used. But for now, I'm not going to talk about them, but yes, they can also be used as a PRNG. So, let's go into one of the an example of one of these PRNGs, and this is going to be a purpose-built algorithm. So this algorithm was designed solely for being a pseudo-random number generator. So that algorithm is the linear congruential generator. So it was first proposed by Lemmer. It's parameterized with four numbers: m, which is the modulus; a, the multiplier; b, the increment; and x naught, which is the starting value or the seed. So the way it works is that you give the seed to this equation over here. You multiply it by a, add c to it, and then you take modulo m, and that's going to be your random value. And then you put this back into here again, multiplied by a, add c, and then modulo m, get your second value, and so on. So this just keeps going and going and going. Now, of course, these values, a, c, m, and your starting value x naught, these are going to be the critical design parameters here. I'm not going to go into what these design parameters are, and what the value, what the optimum values of these are. But you can see, for instance, we want m, the modulus, to be a large number, right? Because when you do modular arithmetic, mod m, these random values, xn, will fall between 0 and m, right? So if m is a small number, then your xn will have, like a very limited set to be in. For instance, if m is 10, xn will only be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So it won't be hard for the adversary to pick out, the random values that were generated. Whereas if m is 1,000, then it's much harder for the adversary. So there's some criteria here that has to be satisfied. But like I said, I'm not going to go too far into it, because it does, it will get, we'll go off track, and we don't want to do that. One of the other, solely based pseudo-random number generators is the Blum-Blum-Shub generator. It's the strongest public, it has the strongest public proof of its cryptographic strength of any purpose-built algorithm. It's a very strong PRNG. And the way it's cryptographically secure. Now, what that means is that if k bits of your output sequence are there, you've already generated k bits of it, there is no algorithm for this generator that will tell you what the next bit is going to be with a high probability, right? In other words, if I go down here to the whiteboard, and if I have a sequence of 100 bits already generated by this BBS, so generated by BBS algorithm, or not algorithm, PRNG, there is no algorithm that will tell me what this next bit is going to be with a high probability. In other words, I really don't know if this bit is going to be a 0 or a 1. There's a 50-50% chance for me, right? No algorithm will tell me that with 99% it's going to be a 0, or with 99% it's going to be a 1, right? There'll still be a 50-50 chance on either output. So this is what we mean by cryptographically secure, right? And it's based on the same property that the RSA algorithm was built, and that's basically factoring an integer into its prime values, or its prime divisors. And the way it works is pretty simple. So if we go up to the slides here. So what you do is you initialize it with a seed. What happens is it squares and then takes mod n, and then it takes the least significant bit. And then it takes that generated value back here, squares, mod n, and then goes again, square, mod n. And every time it squares and then takes mod n, it takes the least significant bit. Very simple approach, but you can see that even the simple approach, you still don't know what the next bit is going to be. In fact, there's a slide here that we have that has a example of it. So let's say my initial seed is 20,749. Although I don't know what the n value for this is. I think it's somewhere in the textbook, but I can look it up later on. It squares and then mod n, and then the output is going to be 143,135. The least significant bit of this is going to be a 1. It takes this value and then squares it again, and then mod n. Again, least significant bit is going to be 1. Square, mod n, get this value, least significant bit 0, and so on. And it's not hard to find what the least significant bit is going to be. If it's an odd number, the least significant bit is going to be 1. If it's an even number, the least significant bit is going to be 0, right? And so you can see this string of generated bits, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1. You can see, we have a run of 2 bits, another run of 2 bits, run of 3, a run of 4 zeros, and then just a single 1, a run of 2, a run of 3 ones, 0, 1, and then a 0 again. And this can keep going on. You can keep going on for whatever number of length you want, right? But you can see, simple approach, how it can be pretty secure. Now, there are many other, purposely built PRNGs out there. There's tons of them. You can read a lot of research papers on this. I'm not going to go into all of them for you because it's a whole topic on its own, and there's certain things that we have to cover if we want to get into them. So I'm going to leave this group of PRNGs, solely built for random number generation. And we're going to move into the ones that we use other structures to build a PRNG. So, if you remember what we had in chapter 7, where we were talking about different modes of operation of block ciphers, there were two modes that that we could use, or maybe even more than that. I think three modes where we could actually use the mode of operation not just for encrypting data, but we could also use it as a random bit generator, right? And here we have two of them because these were recommended, and these are now recommended in certain standards. We have the CTR mode and we have the OFB mode. So this is the counter mode, if you recall that, and this is the output feedback mode, if you recall what they are. And in fact, we actually do have them here as well. So, this is our CTR mode. This is, our counter starts with a certain value. We encrypt it with a key, and this is going to be output. And then we take that value, we increment it by 1, and then encrypt, increment it by 1 again, encrypt, increment by 1 again, encrypt. And this will be whatever we get as the output is going to be our string of pseudo-random bits. In the output feedback mode, what we were doing is, we had a nonce, we encrypt, and then we take the output of the encryption, we bring it back again, we encrypt, we bring it back again, encrypt, bring it back again, encrypt. It's only the first part that we have a nonce, and then we get our pseudo-random bits. And so these are the two modes that are in our standard, and we are going to be focusing on these. We're going to do a little bit of analysis on them. We do actually have a few examples that you can see where how random the generated bits actually are. We'll talk a little bit about them, but this is going to be the end of the second part of the lecture, and then we'll pick up in the where we leave right now in the third part of the lecture.